All right, Matt, we got lesson 3-7, last lesson in this unit, and we're going to do some graphing scenarios. Okay, let's see what we got. We got Hayden walks home from school for 30 minutes, and she takes a 2-hour nap. Then she walks back to school for her choir performance. Sketch a graph showing the distance from school as a function of time. So how far she is from school is going to be caused by time. So if distance from school is a function of time, that means distance from school is going to be the y value, and time will be our x value. Said differently, y is the dependent quantity because her distance from school depends on how long she's been walking for, the time. All right, label and scale the graph. Okay. So if I label this graph, I know the x should be time. Now, if I do it in time, maybe I do it in, I don't know, hours? Time in hours? That could work. Time in hours. So I've got 30 minutes, 2-hour nap, walks back to school. So maybe I would make like this be 1 hour, this be 2 hours, this be 3 hours, and this be 4 hours. So that maybe it would be how I scale that graph for this, just to make sure everything's showing up. Okay, and then my y value is the distance from school. Now, they don't give me a lot of information on how far she actually walked. So we're going to kind of have to, I don't know, make some like assumptions. Like if you're walking 30 minutes, how far are you going to walk in 30 minutes? Would you walk like a mile? Maybe a mile and a half in 30 minutes? Does that sound good? Sure, why not? She can go a mile and a half, 3 miles an hour is pretty good walking. Yeah, okay. Okay, I think I figured it out. All right, so I'm going to make it that she's walking a mile and a half. That's how far away her home is. So I'm going to do it like this. Okay, so that's a quarter, a half, 3/4, 1 mile, a quarter, a half, 3/4, 2 miles. All right, see what I did there? So I've decided on a scale of the graph. And this problem doesn't give us a lot of detail. We're just using our imagination. All right, so we've done our imagination. All right, distance from school. She walks home from school. So when she starts, where's she at on this graph? She starts at school. Where would her distance from school be when she starts at school? It would be here at 0. Okay, and then that first half hour, so this is an hour, so half an hour is to here. She makes it all the way home. And we're going to say that she makes it like a mile and a half home. So that is her going from here to here. There she is at school. For half an hour, she walks home. So she's at home right now. And then she takes a half an hour nap. Now, unless she's sleepwalking, she's not moving during her nap. So let's say that she's not a sleepwalker. She's going to stay at home for an hour, then another hour. So there she is, staying home, taking a nap, not moving at all because she's not a sleepwalker. So she stays home, and then she's like, oh no, I've got to go back to school. I've got to acquire a performance. Parents aren't driving me because it's like 1982, and parents don't drive people in 82. All right, so then she goes back to school. And that's what the graph would probably look like. Something like that. Maybe not exactly. I did connect everything because she's not teleporting. She's always somewhere. So we connected all of our lines. So it shows that she's not teleporting because we can't do that yet. So we've got, there we go. Okay, so there she is. She's going to home. So now she's a mile and a half from school. She takes a nap for 2 hours and then goes back to school. All right, what would the graph have looked like if we made total distance traveled be a function of time? So we did distance from school. What would the graph look like if it was total distance traveled instead? So we're just keeping track of how much distance that she traveled instead of how far away she is from school. So what would that look like? Well, here's what I think it would look like. I think over here, instead of going down, she would have increased her distance another 1.5 miles. Let's see, 1, 2, 3. I think the graph would have ended up being over here instead. So I think the first part of the graph would have been the same, but then if we were doing total distance, the second part of the graph would have continued because we're just tracking the total distance, not how far she is from the school. So what we decide as our dependent quantity over here will decide what our graph looks like. If we do distance from school, that'll show her going home and then coming back to school. But if we did total distance traveled, she'd be going home, staying there, traveling more back to school, and the graph would have continued going up. So the difference would have been after the nap, the graph would have shown a line with a positive slope. So that would have been the difference there. All right, Isabella just ran a race. Good for her. The graph shows the distance in 500-foot increments as a function of time in minutes. Explain what happened during Isabella's race. So it shows distance as a function of time. So this is distance in feet. And then this is time in minutes, because distance is a function of time. All right, explain what happened in the race. Well, it looks like she started, which is good. So she started down here. She went here, then it flattened out here, flattened out even more. So it looks like the first 1-2 minutes, so that's a 2-minute increment there. For the first 2 minutes, it looks like since this is steep, she went pretty fast. She went 5,000, 2,000 feet in 2 minutes. So it looks like in that first part, she was going pretty fast. So here's what happened. First, she started off fast. For 2 minutes. Then it looks like in this next section, there's 1, 2, 3, 4, 5 minutes. So here from minute 2 until minute 7, that's a 5-minute increment there. It looks like she slowed down for 5 minutes. And then there's a third part of our graph. Oh dear, she slowed down even more in this section. So the steepness is going down, so she's going even slower. And that happened for 1, 2, 3, 4, 5 more minutes. So the last 5 minutes, she slowed down even more. All right, let's see if we can find out how long the race was. So that's total distance. So let's see, these are in 500 increments. So this is 1,000, this is 2,000, 3,000, 4,000. Is she done yet? Nope. 4,500. So this is 4,000. This end of the race right here, this is halfway in between there. So the race was 4,500 feet. Not quite a mile. How many minutes did it take her to complete it? It looks like it took her a total of, from 0 to 12 minutes. What was Isabella's fastest speed during the race? That would be this section over here. So the speed would be the distance divided by time. So that would be like the slope. So her distance was 2,000 feet for 2 minutes. And usually when we give a speed, we give it as a unit rate, meaning I would do 2,000 divided by 2. So that would be 1,000 feet per minute. So that was her fastest speed. That was this section here. Her slowest speed is over here. And in this section, she only went 500 feet in 5 minutes. So she went from here to here. So that's only an extra 500 feet. And it took her 5 minutes to do it. Maybe she like twisted her ankle or something. Let's give her the benefit of the doubt. She got hurt. So we got the slowest part of the race. She did 500 feet in 5 minutes. So as a unit rate, that would be 100 feet per minute. So she was going 10 times as fast over here, and she really slowed it. Yeah, she must have hurt herself. There's no way. Or she just started off too fast. Approximately how many minutes did it take her to travel 3,000 feet? All right, 3,000 feet is right here. All right, we're going to have to guesstimate. Okay, so 3,000 feet. I'm going to call it, let's call it 4.3 minutes. Just because it sounds cool. All right, so about 4.3 minutes. We'd have to write an equation, actually solve for it to actually find out what that number is. But, we can guesstimate on our graph. Here's 3,000. And we can go down here and find our time. Somewhere between 4 and 5 minutes. We'll just call it 4.3-ish because that feels pretty good. Let's do that. All right, almost done. Make a sketch of the scenarios. Throwing a softball. The height is a function of time. All right, so we're supposed to make our own graph. Height is a function of time. All right, if I'm throwing the softball, time would probably be seconds. And the height would probably be feet, or if we're in Europe, we'd say meters or something like that. So we'll say the height in feet. All right, so what would the flight of the softball be? Now, if you're throwing it, you'd probably start by throwing it somewhere near your head. So you'd start up here. Would it go straight and then straight? Probably not. Gravity would probably happen. So we do here and maybe there. That's what the ball would do because gravity would affect it. Now, if I stopped it right here, that would indicate, oh, somebody caught it because that's why it didn't actually hit the ground because at 0, it would hit the ground. Now, if that person threw it and nobody caught it, then we would make the graph keep on going and show that it hits the ground. So it depends on what you want to do. Do you want to assume that, hey, somebody caught the ball right here? Sure, you would make it stop right about there. If you want to show that somebody didn't catch the ball, you'd let the ball go all the way to the ground. Sweet. A cup of hot tea cools down quickly at first, but then slows down as it gets closer to room temperature. All right, so the temperature of the tea is a function of time. This would probably be minutes, with time on this one. And then over here, this would be the temperature of the tea. We'll say Fahrenheit. If we were in Europe, we'd say Celsius or whatever. So this one says that it cools down quickly at first and then slows down. So since the speed is changing, this is not going to be a line. This will be some kind of curve. So if it goes quickly at first, we might do something like this. It goes quickly at first and then slows down as it approaches room temperature. So this might be our graph. This part here indicates where room temperature would be, because it cools down quick, and then as time goes by, the temperature gets closer and closer to room temperature until eventually it'll hit that room temperature right there. So that would probably be some kind of curve that we would do. All right, that was fun. Hope you enjoyed it. Keep on mathing, and I will see you next week. Goodbye.